Hello, my name is Reese Allen, and this is my lab for final submission. So for an intro to the lab, we use a circuit construction kit that was given to us to create many scenarios that involve batteries, capacitors, and light bulbs, as well as using ammeters and voltmeters. For measuring, we use these voltmeters and ammeters to measure voltage and current respectively, and the goal was to primarily relate change in voltage to a time constant, RC, which we calculate at the end of the lab. So for the initial portion of the lab, we create our first circuit. And this first circuit is one with 2 batteries, 2 ammeters, and 2 resistors, one with 47 ohms and one with 100 ohm. The purpose of the circuit was to test different functions of the construction kit and see how the ammeters and voltmeters actually work. So the first test we did was setting up 2 ammeters on opposite sides of the circuit, and we see they read the same values as the current is constant throughout the whole loop. And when we turn one of the ammeters backwards, it reads a negative value. So then we replace one of the ammeters with a voltmeter to measure electric potential across the circuit at different points. And below I have a graph that reflects the total voltage as we move across different points along the circuit, which ends up being to 0. So after creating that first circuit, we were able to solve for some values that more relate toward resistance. And so by solving delta V over I for different parts of the circuit, where I is the current of the circuit and that delta V is the change in electric potential across a certain point, 2 points, we're able to solve for the resistance of the 100 ohm resistor, the 47 ohm resistor, the wire, and the ammeter. So the resistance of the 100 ohm resistor ends up being 102.05 after dividing that change in electric potential over 0.02, which was our current. And for the 47 ohm resistor, we get 47.95. And the wire and ammeter don't have any change in electric potential, so that just goes to 0. And then, so for the next portion of the lab, we create a new circuit. This circuit has a 10 ohm bulb, a 200 millifarad capacitor, and a 9 volt battery. We make some observations here in that the circuit with the light bulb, it turns on brightly as the capacitor charges, and then begins to dim out and turn off as the capacitor reaches full charge. And the same goes for when it is discharged, taking out the battery in the circuit. The light bulb was on until the capacitor fully discharges. And then some measurements were taken for the time it took to charge and discharge. So for the 10 ohm light, I recorded that the capacitor took 3.57 seconds to charge and 4.17 seconds to discharge. And then we did the same thing for the 20 ohm light bulb, and we see that it takes a little longer in both of those measurements respectively, in that it took 4.8 seconds to charge and 7.83 seconds to discharge. So for the final portion of the lab, we set up our RC circuit. This circuit connected a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb. So to start, I charged the capacitor by starting the circuit, allowing it to reach full charge. And the initial measurement was taken at 9 volts across each node on the capacitor. This was my V0 value. And then for data in my experiment, I used an Excel file to create a plot of ln of delta V over V0 versus time. So to do so, I recorded the electric potential of the capacitor as it discharged at each second on the interval 0 to 20 seconds. And the graph looked like it does below, with a slope of negative 0.167. And this slope we can relate to the time constant of negative 1 over RC, which results in a value of 5.988 for RC, which is very close to what was predicted at 6. So to conclude the experiment, there are 2 major questions that we want to reflect on. The first is, what if you were doing this lab in real life, use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So the real ammeter would have had variability, as it does provide some resistance in real life. The ammeter would create a slightly different value in real life, and in the idea model, the ammeter provides 0 resistance and just reads the current values going through the circuit. So the second question we want to ask ourselves is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the current? How quickly would your ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So in real life, the battery also has some sort of internal resistance that would restrict the 9 volts of moving through the circuit as fast as it would in the ideal simulation. Had we used it in the circuit with a capacitor and no resistor, the capacitor would take more time to charge than the ideal model due to an due to the internal resistance that is included in the real model. All right, thanks.